Hi, my name is Ravi Narayan Swamy and I work at Intel. I've been participating in the definition of OpenMP since they started introducing accelerator and device support into the OpenMP spec. Just one note, everything I'm expressing here in this tutorial, in this presentation are my own, and I'm not speaking for my employer. Okay, let's move on to the agenda. So I'm going to start off with the motivation. Uh, and then I'm going to talk about the main topic, which is the declare variant and the dispatch, the theme of this presentation. And I'm going to conclude with the example. So the motivation is basically we want to have interoperability with the libraries. So we want users to be able to use OpenMP constructs in their application, but have the ability to call specific libraries, optimized libraries, which may or may not use OpenMP offloading. And so you want to be able to interrupt and share data. You want to use, the user might send some data to the device, and then you want the libraries to work on that data, and then you return back to the user, and then you want to bring it back. So you want to have the ability to share this data with the thing, OpenMP. And so for that, we have introduced two new features. One is declare variant, which is already existing, but we have enhanced it with some additional clause. And in 5.0, we had the declare variant. And the declare variant had a single form, which was the sequence of declare variant with just a match clause. Now we have added additional argument clauses, which is the adjust arg and append arg. I'll talk about more about these two arguments, two clauses. And so the way it works is just as an overview, you have declare variant, a sequence of declare variant, and each of them will have a match clause. So the match specifies under what condition you would replace the function which is following this declare variant, which I call the base function. What function replace the base function under what condition? And the two new clauses will give you the ability to do some manipulation of the arguments. So the other new one we have introduced is the begin and end declare variant. So all the functions in this declare variant provide an alternate to a base function which is defined somewhere else. And there's a naming scheme where you can name these functions as a replacement instead of using the base function. And they are basically based on the context selector, the naming of that. So moving on to the clauses. So as I said, there was initially in 5.2 the match clause. Now we introduced the adjust arg and the append arg. I'll explain more of these. So basically where the adjust op is either you can have nothing or need device pointer. So these are the two currently provided ones. And the append arg is where you can append an argument like an interop argument. And the variant function, which is defined in the variant function, is the specialized function, or what we call the variant function, which will be used instead of the base function, function name. So similarly in FORTRAN, you have the declare variant. But one thing you notice is in FORTRAN language, you cannot have anything in the global scope. You cannot have any pragmas in the global scope. So you don't see that begin and end variant versions of the thing in FORTRAN. You just have just the declare variant, which can be used inside a function. That's because of the restriction, the way the language is. So next, moving on to the match clause. So match clause gives you the ability to selectively replace the original function with the variant. The other key function is that you can write code which only your compiler can recognize, and will be skipped by other compilers which don't recognize that code. So let's say you want to use some customized inline ASM or intrinsic, and your compiler supports it, but other compilers don't support it. But you want this compiler, this code to be portable. So you can use these match clauses to selectively elide this code by other compilers, but only your compiler can recognize it. So here are some examples of the match clause. So the first one, you have a match and you have a context dispatch. So basically, this is saying anytime I encounter a dispatch construct, replace the call in that construct with this variant. So the next example is where you want to say, oh, when you're compiling for this architecture gen, then compile this code, else skip this code. So this is where you could use gen-specific optimizations or assembly or intrinsic, and other compilers can skip that code without having any syntax errors. And then the other one is where you can use a kind no host. So basically, you want to have specialized code for host or for the device. So when you specify no host, basically that code will be enabled, or that variant will be enabled only when you're compiling for the device. And when you're compiling for the host, that code will be skipped. And similarly, when you specify a kind host, the code which you use here will be skipped, and only for the, I mean, will be skipped for the device, but will be used for the host. So next, I mean, so now the clauses, I'm going to go dive a little more into the thing clause. So the append clause. So append clause provides you the ability to add additional arguments. So the first, I mean, currently we only allow the interrupt operation construct to provide an interrupt type, add an interrupt type. And I'm not going to go too much into details on this interrupt object. I would recommend you to watch the talk by Tom Skoglund on the interrupt construct, which will also be available on the OpenMP website. So the way it works is the argument is constructed as if an interrupt object, interrupt construct was encountered with an init clause. And the arguments are passed in the same order as they are specified in the variant function. And once this construct for the variant is completed, this object is destroyed. So these are the simple rules, but a lot more details you can attend the other, watch the other presentation where Tom will go into much deeper details of how the interrupt object works. Next is adjust argument. So the way you want to do is, suppose you transfer some data onto the device, and now you want to pass that device pointer to your library. So you have the ability to say adjust the argument and say that this argument I need it to be a device pointer. So the way it works is, if the argument provided as an host pointer, we would translate it using the use device pointer and look up and find the device pointer. So the device pointer will be passed. If the argument is already a device pointer, then it is not modified, it's just passed as is. And in case you cannot modify it because the device pointer does not, the corresponding device pointer on the device does not exist, then you would be passing a null value, where the variant function can check if it's a null value, then there's something wrong with the conversion to a device pointer. The user can also say, adjust or modifies nothing. So basically, this implies don't modify the argument, pass it as is. Okay, the next key feature which was added to enable this is the dispatch variant. So the syntax for this in C++ is you have a OMP dispatch construct followed by an expression statement. And the expression statement is essentially a assignment of a call to some expression or a call. And the clauses you can specify for this construct is the device, depend, no wait, no variant, no context, and device is device pointer. So the device, depend, and no wait, and is device pointer already existed in 5.2 on a target construct. The two new ones are the no variant and no context. So device is essentially saying you want the you want whatever the memory. When you say use device pointer, you want that device pointer for that thing to translate that memory argument. So similarly in FORTRAN, you have the OMP dispatch, and same as C, you have all these things, but except it's like a call, target call with arguments in FORTRAN. And okay, so the dispatch clause. So the way it works is if no variant clause is present uh, and it evaluates to true, that means you would not substitute the call following this dispatch construct. So you'll be just calling the base function. If the no context clause is present and evaluates to true, the dispatch construct is not added to the construct set of the OpenMP context. And is device pointer indicates that it's already a device pointer, so you just pass it as is if the user has requested in the variant function that he needs a device pointer. And the no wait allows you to execute this construct asynchronously by adding it to the interop requirement set. And the depend clause enables you to have dependence between other tasks, and so you can be added to the it'll be added to the interrupt requirement sets. Okay, so now let's go on to the examples. How would you? I mean, earlier before without these new features, you would probably do selective coding using IFDEFs. So you would have an IFDEF host. So essentially saying if when you're compiling for host, use this routine. Else you're compiling for something else, use this function. They have different behaviors. Now, the problem with this is that you need to standardize what the defined macro is. So all the compilers need to know, oh, host means this host function or CPU, and else part will be other devices. And then you could, I mean, you would want to also customize for different architectures, but this doesn't provide it. In a sense, it can provide it by using IFDEF, host, or architecture, blah, and vendor, something else. So you could have a bunch of things, IFDEF macros. But then again, you have to standardize all that. So you would need to coordinate with all the other compiler developers or have some sort of standard to be able to define this. The other thing is that with this IFDEF, any call which is calling this routine will get replaced in the code. You cannot selectively say only in this section of the code I want it to be replaced and not replaced in other calls. And so an example would be when you're compiling for the host and any host calls you want to do you don't want to do a replacement, but when you're compiling for a target, all the target calls you want to do a replacement. So it doesn't provide you that capability with the IFDEFs. So you can basically use the OMP declare variant construct to get this functionality. So here you have a declare variant, and I say when match device is host, right? Then use this function. And then I have another declare variant when the device is no host, then use this. So all OpenMP compatible compilers will be able to handle this construct. So it's already sort of like it's standard now. So you don't need to go about trying to define macros to standardize that. And the thing is that when you're compiling for the host, this code is selected and this code is skipped. You completely ignore this code. And when you're compiling for the device, you just consider the code which has the kind no host, and you skip this code which has the host. So now here's an example of how you would use all these variant dispatch function. So let's assume you have a math library, my math library, and you have a SGEM, which is a customized GPU routine. So you have your regular arguments, and then I have an additional argument interrupt object here. So I want to replace all the calls of SGEM with the SGEM GPU, and I want to do it selectively. I don't want to replace every call, but I want to say when the function is under a dispatch construct, and your offload device is gen, and you do the replacement. And once you select for replacement, now I want you to give me the device pointers for A, B, C. So the first three arguments, I want the device pointer, and then I want you to append the interrupt object. So when this function is used under a dispatch construct, and you're compiling for architecture which is gen, then you would replace the arguments A, B, C with the device pointer and append an interrupt object and call this function sgem-gpu. So now let's see how it works in the user code. So here's a program in the user code. You would include your math.h, which has that declare variant function. So you have four variables, and then you would initialize these, and then you would call sgem abc. This is now this doesn't match the variant because this is not under a dispatch construct. So this does not get replaced. So here you'll be calling only the host version. Next, you enter the target data, and then you map all these three variables onto the device on a device where device ID is something. And then you would have, now you want to replace all the, let's say you want to call the specialized version. So you would say pragma OMP dispatch device and put in the device ID, and then you provide this function. So now that variant automatically kicks in and replaces this and uses the device pointers. So these were already mapped and sent on to the device. So here you would query and get the device pointers, and you would call the specialized device version. You'll call the GP version. And similarly, you can repeat that again, but pass something different, call the device version. And so that concludes my talk, and just want to mention that all the recording and the slides will be available on the OpenMP website. Thank you.